Alright, so today we're going to have a look at our new topic, further calculus. So further calculus is, in my opinion, one of the more exciting topics in the course, and we look at different ways of differentiation, but more importantly we delve deep into integration and how we integrate harder things than what you might see in the advanced course. So in today's video, we're going to have a look at the differentiation of inverse trigonometric functions. So often we like to think, okay, why am I doing this? Why would I want to differentiate an inverse trig function? Well, on things like a professional sound mixer, we deal with something known as panning. So panning is, to the best of my knowledge, moving the audio from one side of the room to the other. So it's almost like surround sound. It's moving audio from left to right in maybe a system of speakers or a single system. It's moving the audio around the room. Now often you'll see a panning knob or a little display from -1 to 1. Now, if you're wanting to automate certain panning movements, it may be useful, and it might just look like it's a simple press of a button. But what the machine actually is doing is differentiating an arc sine function, so a sine inverse function, to achieve a particular angular rate of change. Now, while you may think you're just inputting a simple parameter into a machine, which is what you are doing, in the background, the machine is really analyzing a complex wave function. And this is particularly relevant when a single speaker produces the illusion of surround sound. So the differentiation of sine inverse of x, or arc sine of x. So if we let sine inverse of x equal to y, then taking the inverse of both sides, we get x is sine y. So we're swapping that x and y and then making x the subject. Now if we differentiate that dx to y, we get cos y. Now the reason it's dx to y and not dy dx is because in this instance x is here, so x is the subject of our equation, and it's in terms of y, so the y is on the bottom. Often that's the opposite of what we usually see. Now because of that, we know that cos y, well, cos squared x plus sine squared x is equal to 1. So that would mean that cos y is equal to the square root of 1 minus sine y squared. But we've said that sine y is equal to x, so cos y is equal to the square root of 1 minus x squared. But at the same time, we've said dx to y is cos y. So that tells us that dx to y is equal to what cos y was, 1 minus x squared. But we don't really care about dx to y, we want to know dy dx. Flip it upside down, we take the reciprocal, and we get 1 on the square root of 1 minus x squared. So therefore, d by dx of sine inverse of x is equal to 1 over the square root of 1 minus x squared. Okay. We're going to do that together, and we're going to find the differentiation of cos inverse of x. So the first step, as was the first step of the last one, is to let y equal, this time it's going to be cos inverse of x. Taking the inverse of both sides, that would tell us that x is equal to cos y, and differentiating that, dx dy is equal to minus sine y. That's because the differentiation of cos x is minus sine x. Now we know that sine squared x plus cos squared x is equal to 1, so that would tell us that sine of y is equal to the square root of 1 minus cos squared of y. If you did cos squared x plus sine squared x, rearranged it for sine y, we would get that. But we've said x is cos y. So sine y is equal to the square root of 1 minus x squared. But we've already said that dx to y is minus sine y. And we know just now that sine y is the square root of 1 minus x squared. So that would tell us that dy dx, or dx to y, is equal to minus 1 minus x squared. In other words, we want to know dy dx, we flip it upside down, so dy on dx is equal to minus 1 over the square root of 1 minus x squared. So there we go. d by dx of cos inverse of x is equal to minus 1 over the square root of 1 minus x squared. Now that's the opposite of what we saw, not really the opposite, but it's just the negative of sine inverse of x. So the formulas are very, very similar. Cos inverse of x has just got a minus in front of it. Okay, the odd one out, tan inverse of x, not really that much different, but it's not going to have a square root on the bottom. So let's follow the same process. We know that x, or we might say let y equal to tan inverse of x. And that would mean, taking the inverse of both sides, x is tan y. Now let's find dx dy. Hopefully we remember from advanced that the differentiation of tan is sec squared. So this is sec squared y. Now we also know that sec squared y would equal 1 plus tan squared y. That's back to one of our advanced properties, which means that sec of y is equal to the square root of 1 plus tan squared y. But we've said that x is tan y, so sec of y is equal to the square root of 1 plus x squared. Now we know that dx dy is equal to sec squared of y, and we also know that sec y is the square root of 1 plus x squared. So if we square that 1 plus x, root 1 plus x squared, we get 1 plus x squared without the square root. So that means dx dy is equal to the square root of 1 plus x squared, all squared, which is 1 plus x squared. But again, we don't care about dx dy, we want dy to x. So we flip it upside down and get dy dx is equal to 1 over 1 plus x squared. Right, so therefore our formula is dx on dy of tan inverse of x is 1 over 1 plus x squared. So those are our three formulas there. So the differentiation of sine inverse of x is 1 over the square root of 1 minus x squared. Cos inverse of x is the same thing, but with a minus out the front. And tan inverse of x, our differentiation, is 1 over the square root of 1 plus x squared. Okay. Now, these are the formulas that we need to remember. Now, this is technically called the reverse chain rule, but I like to just think about it as our formulas for differentiation of inverse trig functions. So, our formulas are, if we've got sine inverse of x, on the top we're going to have f dash of x, and on the bottom we've got the square root of 1 minus f of x squared. So what that tells us is if we have an inverse trig function, we're going to differentiate what's inside the brackets and put it over the square root of 1 minus that thing squared. So we're going to determine d by dx of cos inverse of x of 3x squared plus 2. So on the top is going to be the differentiation of 3x squared plus 2, which is 6x over the square root of 1 minus the thing in the brackets squared, 3x squared plus 2 squared, and because it's cos we need to put a minus out the front, and we're done there. Now there's no real point at the moment in expanding and simplifying this, I'm fine we just leave it like that. Okay, determine d by dx of sine inverse of ax plus b. Again, we need to differentiate what is inside the brackets and put that on the top. So the differentiation of ax plus b is a over the square root of 1 minus ax plus b squared. It's as easy as that, ax plus b squared. Question number 3, we're finding the differentiation of tan inverse of x cubed plus 2x squared plus x plus 1. Again, we're going to differentiate what's inside the brackets, so that's going to be 24x squared plus 4x plus 1 over 1 plus the thing in the brackets all squared, 8x cubed plus 2x squared plus x plus 1, and we're squaring that. Awesome, nice and easy. Alright, Now we're going to use our knowledge of our advanced differentiations, and the product rule is going to be relevant here. So we're finding the differentiation of x times by tan inverse of x. Importantly, we can't do this. It's not going to be x over 1 plus x squared. We can't do that because we've got two functions multiplied by each other. So we're going to have to use the product rule. So the product rule states that we differentiate the first thing and times it by the second thing, and then we add the differentiation of the second thing multiplied by the first thing. So the differentiation of x is 1 times by tan inverse of x, so we've just got tan inverse of x, plus we differentiate the second thing, 1 over 1 plus x squared, and times it by the first thing, x. So therefore the differentiation is tan inverse of x plus x over 1 plus x squared. The question here says we're going to find the points A and B on the curve y as cos inverse of x minus 1, where the tangent has a gradient of minus 2. So we first of all need to think about, okay, what does it mean when I've got tangents and gradients? From our advanced knowledge, that means that we're going to differentiate and find when it's equal to minus 2. So let's differentiate that. So the differentiation, d by dx, of cos inverse of x minus 1 is equal to the thing on the top. We differentiate it. So differentiation of x minus 1 is 1 over the square root of 1 minus x minus 1 squared, and we put a minus up here. Now we're asked to see when does that equal minus 2. So that equals minus 2. Okay, this is then going to end up being a quadratic equation. We'll have a think about solving it. So we might square both sides. So 1 over 1 minus x minus 1 squared equals minus 2 squared is 4. So we square minus 1, we get 1. We square the bottom, the square root dies. We square minus 2, we get 4. Let's times everything up to the other side. So 1 is equal to 4 minus 4x minus 1 squared. And then we're going to expand that. So 1 is equal to 4 minus 4x squared. It's going to be plus 8x minus 4. Those 4's will die, and we're going to have 4x squared minus 8x plus 1 is equal to 0. I think, yeah, 4x squared minus 8x plus 1 is equal to 0. So x is going to equal 8 plus or minus. Let's get my calculator for the discriminant. Square root of 8 squared minus 4 times 1, which is 48. That doesn't seem right. 4 times 4 times 1. Oh, no, that's right. Plus or minus the square root of 48, which is 3 root 2 over 2 times 4 is 8. So x is going to equal 1, not 3 root 2, sorry, 4 root 3. So x is going to be 1 plus or minus root 3 on 2. So we've got 1 plus root 3 on 2 is our first point with some y point, and then 1 minus root 3 on 2, and then some y point. I'm going to have a go at substituting that in. So 1 plus root 3 on 2 is equal to, put it in radians, cos inverse of that, we get, maths error, 1 plus root 3 on 2 minus 1, we get pi on 6, and put the minus 1 in there, we get 5 pi on 6. So those are our 2 points there. Okay, now we're going to sketch this curve showing the 2 points. So we're trying to sketch cos inverse of x minus 1, and we're going to add those 2 tangents in. Okay. So cos inverse of x minus 1 is just our normal cos inverse graph, but moved over by 1. So normally our cos inverse graph looks like this. So it goes from 1 to minus 1. This is pi on 2, and that's pi up there. But if we have cos inverse of x minus 1, it's going to be that same graph to move over by 1. So it's going to be that graph there. If we move it over by 1, this becomes 2, and this 1, minus 1, goes over to 0. So we can delete that blue graph now. Right, so we've got 1 plus root 3 on 2. Now 1 plus root 3 on 2 as a decimal is 1.86. So 1.86, let's say it's about there. 1.86. So that's our point A with a gradient of minus 2. And then 1 minus root 3 on 2 as a decimal is 0.13. So it's about here. So that's our point B there. So there we've labelled our graph and we've added the 2 points. Now when it says show those 2 points, it means show the gradient of minus 2. So we've shown at these 2 points the gradient is the same, and we've expressed that by drawing 2 straight lines that appear to have the same gradient. Okay, we're going to differentiate d by dx of tan inverse of e to the minus 5x. Okay. We might just to the side recall what the differentiation of e to the minus 5x is. So when we differentiate e to the anything, we differentiate what the power is and we bring it down. So minus 5, and then we just leave this thing the same. So minus 5e to the minus 5x. So applying our rule to differentiate tan inverse of x, we differentiate what's in the brackets and we put that on the top. E to the minus 5x over 1 plus the thing in the brackets squared, e to the minus 5x squared. Now we can simplify that and write this as minus 5 e to the minus 5x over 1 plus e to the minus 5 times 2 is 10x. That's the differentiation there. Okay. We're going to sketch cos inverse of cos of x. When we're trying to sketch these graphs, we're going to start using our knowledge of calculus. So the first thing we might do here is we're going to differentiate, and then we also might use a table of values if that doesn't help us. So let's go d by dx of cos inverse of cos x. So again, the way we differentiate cos inverse is we differentiate the thing in the brackets and put it over 1 plus what's in the brackets squared. So if we differentiate cos of x, we get minus sine of x over sine of x over the square root of 1 plus the thing in the bracket squared, 1 plus cos squared of x. And because this is a cos inverse differentiation, we need to put another minus out here. Now that really just gets rid of both of those minuses there. Okay. And there should be, that should be 1 minus cos inverse of x. That's our formula, 1 minus the thing in the bracket squared. Now 1 minus cos squared of x is sine squared of x. That's using our cos inverse. Cos squared of x plus sine squared of x is 1. And doing that minus, we get sine squared of x. Square root sine squared of x, we get sine of x. So this is equal to sine of x on sine of x, which is 1. But when I square root something, I can get a plus or a minus answer. So this could also have been sine of x over minus sine of x. The square root of sine squared of x is plus or minus sine of x. So this could have been minus sine of x on the bottom. Now that will give us minus 1. So therefore, d by dx of cos inverse of cos of x is plus or minus 1. Now we're thinking, okay, how can I have two constants as my differentiation? That doesn't really make any sense. Because of that, we're a bit stuck. Now, a graph that has a gradient of 1 is really just like the line y is x, and a gradient of minus 1 is the line y is equal to minus x. So what we might do is draw a table of values to try and aid our understanding in that. So x and y, and we might substitute in, let's say, 0, pi on 2, pi, 3 pi on 2, and 2 pi. Those are really our critical points on any trig graph. If you substitute in 0 into our equation, you get 0. Pi on 2, you get pi on 2. Pi, you get pi. 3 pi on 2, you get pi on 2. And 2 pi, you get 0. Let's graph those critical points. 0, 0, pi on 2, pi on 2. We might say this is pi, and this is pi on 2 up here. Pi on 2, pi on 2. So we might say this is pi on 2 here, and this is pi here. So we've got pi on 2, pi on 2, pi, pi, 3 pi on 2, pi on 2, and 2 pi 0. And because cos and any trig graph really is symmetrical, we can say that, or not any trig graph is symmetrical, but cos itself is symmetrical. It's going to look like this. And we've got a gradient of 1 or minus 1, so these have to be straight lines. It's the only way they're going to have a gradient of 1 or minus 1, as if these were straight lines. So that's our graph there. Alright. Last example for this video. So we've got, consider the function y is equal to cos inverse of x squared. Now we're thinking, what is the domain of f of x? Now, the domain of x squared is all real x, and the domain of cos inverse of x is minus 1 to 1. Now we should know from our inverse functions topic that the domain of the function cannot be any greater. So if you put in x squared, the gradient of the whole function can't be any greater than the original function. So x squared is not going to magically make cos inverse of x bigger than its original domain. But since the domain of x squared, so the domain of x squared is from minus infinity to infinity, so the domain of x squared is from minus infinity to infinity. And the domain of cos inverse of x is from minus 1 to 1. So therefore, the domain of cos inverse of x squared is just from minus 1 to 1. So the largest the domain can be is from minus 1 to 1. Part B, about which line is the graph symmetrical? Well, let's think about what this graph is going to do. So we know that the graph of y is x squared itself is symmetrical. We also know that cos inverse of x is also symmetrical. But what we also know is that x squared makes any negative number, or we should say any number, positive. So minus 1 squared is 1, 1 squared is 1, minus 2 squared is 4, 2 squared is 4. Any negative number becomes positive. And that means that the absolute value of any x coordinate goes to the same y coordinate. So we might say that minus 0.5 and 0.5 will have the same y coordinate. therefore it is symmetrical around the line y is equal to, around the y-axis, or x is equal to 0. That's because any negative value has to become positive, so minus 0.75 squared will equal a positive number, and it's also going to be the same positive number as when you square positive 0.75. So therefore it's going to be symmetrical about the y-axis. And that's what we would expect. It's the same symmetry that a parabola has. Okay, part C, we're finding the differentiation. So we're finding d by dx of cos inverse of x squared. So our rule tells us that to find the differentiation, we differentiate the thing in the brackets, which is x squared. Differentiate x squared, we get 2x over the square root of 1 minus the thing in the brackets squared. X squared squared is x to the power of 4. That's our differentiation there. Now part D says, show that the f of x have a maximum turning point at x is 0. Maximum turning point at x is 0. From our knowledge of advance, we find turning points by setting the differentiation to be equal to 0. So let's set that to be equal to 0, so 2x on, and we should actually, I just did that differentiation wrong there, we need to put a minus here from our formula, so when we differentiate cos inverse, there's a minus on the top. So minus the square root of 1 minus x to the power of 4, that equals 0. Now we times the denominator up to there, it just dies, so minus 2x is equal to 0, meaning x is equal to 0. So therefore the graph does have a maximum turning point at x is 0. We need to prove that it's maximum, so we know there is a turning point at x is 0, but let's prove that. The way we do that is by drawing a little table of values. So we're going to put 0, we might put minus 0.5 here and 0.5 here. Now officially the way we do prove this is by differentiating a second time to test concavity, but it's going to be quite tricky to differentiate this, so this table of values is more appropriate in this circumstance. What we're doing is we're going to substitute these values into our differentiation to see whether the gradient's positive or negative. So if we substitute in minus 0.5, we get a positive number, so that means our gradient's going up. We substitute in 0, we get 0, so it's a flat gradient. And if you type in 0.5, we get a negative number, so it's going down. So therefore, it's a maximum. Show that f of x is undefined at the endpoints of the domain, and what is the geometrical significance of this? So we look at our differentiation, we get minus 2x on the square root of 1 minus x squared. If we substitute in the endpoints of our domain, so we've decided that the domain is from minus 1 to 1. So if we substitute in minus 1, let's substitute in minus 1, we're going to get 2 times minus 1 over the square root of 1 minus 1, which is 0, so over root 0. So therefore, this can't occur. And if we substitute in positive 1, minus 2 times 1, over the square root again, 1 minus 1 is root 0. So therefore, undefined at minus 1 and 1. Alright. Now I've got to sketch that graph there. So a few things we've decided about this graph. Number one is that it's symmetrical about the line, the y-axis. And we've also decided that it has a maximum turning point at x is equal to 0 on that y-axis. So the maximum turning point here, and it also has endpoints at 1 and minus 1. Now, if it has a maximum turning point, the graph has to go up here, and then it has to turn around and come down here. Now when we made it equal to 0, there were no other turning points. So this is actually our graph here. Now we might want to think about what that, what the value of that maximum turning point is going to be. Well, the normal y-intercept of cos inverse of x is pi on 2, so it's not really going to change. We might want to check that though, so if we substitute in 0 into our equation, we're going to get cos inverse of 0 squared, which is cos inverse of 0, which is pi on 2. There we go. Thank you. Thanks for listening.